Okay, hi. Thank you for being here despite the potential lunch break. There is some statistical evidence that judges make much harder verdicts before the lunch break, because they're hungry. Who is hungry? Don't be too hard to us. Okay, so we are going to talk about technical debt, about some problems with the term itself, and also present ways how to do it better. My name is Konstantin, and with me here is Enes, my colleague. We are not going to define technical debt. We assume somehow that you are familiar with it, with the problem itself. So obviously technical debt is about surprises, but it's also about things that prevent us from developing features. And it is also about miscommunication and misunderstandings between developers and management. Okay, let's start with some statistic. This year is a large study with 1,000 executives and 1,000 developers from 5 different countries, 30 industries. So the values here are quite meaningful. And one aim was to find out how developers spend their time. And as you can see here, more than 40% is spent for maintenance work, like fixing suboptimal code, bugs, which also includes technical debt. And conversely, it means that the efficiency of developers is less than 60%, and that is actually far away from what is considered as ideal in the industry. Clearly, nobody expects 100% of efficiency because there will always be some maintenance work to do. There will always be bugs. So maintenance is unavoidable. But the point here is that you could actually end up with 80 if you do it right. And the point is that one makes its life unnecessarily complicated. And one of the main results of the study was that it's due to the so-called firefighting. It means that problems get out of hand, they accumulate, and cause much more additional work than would be necessary if one tackles them regularly and in time. And we always use this picture to illustrate the problem. Some of you might have already seen similar pictures, so we don't want to reinvent the wheel here. So on the one hand, there is a normal zone where you can stay if you regularly spend this 20% of maintenance effort to tackle technical debt and other maintenance tasks. And through this regularity, you get the chance to avoid escalation of effort, right? However, if you miss these opportunities to work on technical debt a few times too often, you can escalate to the danger zone. And actually, this zone is the most interesting one because the real risk you are exposed to here depends on the trends and evolution of certain quality trends, like maintenance effort, for example, that you actually have to really measure to understand where you are and how often you can afford to do nothing or to do less. Otherwise, you can end up in the end-of-life zone where the problems are so big that they have already a customer impact and maybe the project has failed because you can't always expect to take the lucky path. But actually, all this is well known. And for the most people sitting here, it should be no secret that there is actually this often mentioned trade-off between internal quality and cost. It actually doesn't exist. Some texts about technical debt make a kind of dramatic arc out of the fact that they postulate quality costs just to argue at the end that it actually saves costs. And this statement, if you think good architecture is expensive, try bad architecture, brings it actually to the point. And also, almost everyone understands the problem. That it's like this. There are still problems in real projects to put this knowledge into actions, right? And why that is and how to do it better is actually the topic of this talk. And to do it better, we at Cape of Good Code have developed an own analysis tool that we call Detangle, which brings us to a very short introduction to ourselves. So Cape of Good Code was founded in 2018 by Egon Wuchner. Me, Egon is today not here, but before that, 2013, we met at Siemens, where we started to work on new approaches of software quality analysis because we were not satisfied with the existing tools, with lack of actionable knowledge, with the number of false positives. So we started to work on own approaches, and the result was Cape of Good Code in 2018. We were funded by the Bavarian state to develop the first prototype and start making pilot projects, and in the meantime we have even another funding from them. As to me, I have studied computer engineering in Aachen and became self-employed right after the study, worked in smaller and bigger companies in different roles, developer, architect, lead, technical lead, and at Cape of Good Code I'm still responsible, so I'm responsible for the development of Detangle. I still code like 40–50% of my time, and the rest of the time I'm involved in customer projects. And Enes?
Here is Enes. I have studied engineering in different domains, and as a person who loves to simplify and automate things, I got myself lucky at 2021 and joined the company.
Okay. What we are doing at Cape of Good Code, all different kinds of projects with where the point is to analyze the software. For example, software due diligence is when companies buy each other and want to check the software, but also just normal quality analysis, also known as software audits or architecture reviews, and we also do some workshops about development process and quality analysis. Okay, let's get back to the topic. Let's have a look on how the handling of technical debt happens actually usually in real projects. As you can see in the picture, the engineering team is usually in the middle and has to take care of everything. So it has to deal with technical debt, it has to address it, but it also has to care for the budget for it. It doesn't matter if it's time or money. So it has to convince product owners, managers, other executives of the need to do something at all. So as if technical debt is just a whim of the developers and not a problem that actually concerns everyone. So at the end of the day, the development team has to talk a lot about technical debt to eventually get a chance to fix it, to address it. And what's a big problem there? Well, unfortunately, we as developers often sound like idiots when we talk about technical debt. By the way, this here is a highly recommendable blog article. We could actually have named the entire talk like this, but we didn't want to steal the title. But seriously, seems like there are certain problems with the term itself, with the metaphor. And why is that? In order to understand it, we have to look at some ways how technical debt is usually discussed. Here's one example from Philip Kuchten. So what he does is he divides things that occur in software projects into visible, invisible, and basically good and bad. The green features, of course, they are visible and good. This is why we develop software for. Defects are also visible, unfortunately, and they are bad. Then there is a middle thing here, the yellow one. It's invisible, but it's still good. So it's about some architectural improvements that could be some preparational work for features. That's why they are good. And we have the technical debt, bad and invisible. And the $1 million question is, of course, whether we can convince the responsible, the executives, the money lenders with such illustrations. And the answer is, not surprisingly, no. And the reason is that technical debt is this invisible phenomenon which makes it incredibly difficult to negotiate about it at all. The other problem is all these complicated terms on the right, these technical terms, complexity, dependency structure, architectural depth, that non-technical managers often just don't understand. But let's get back to the invisibility. This is just one problem. And there is another one why the technical depth metaphor doesn't work as one might wish. And in order to understand that, let's have a look on another technical depth quadrant from Martin Fowler. This is a more famous quadrant. Who knows it already? Who has already seen this one? Oh, okay, cool. Then it makes sense to go into detail and explain it. So what Martin Fowler does here is he divides reasons for why technical depth happens into reckless, prudent, and deliberate, inadvertent. So just for the German-speaking people here, it's very important to understand what prudent means. It's umsichtig, besonnen, and yeah, reckless ist rücksichtslos. So let's go through the different cases. Reckless and deliberate technical depth. We don't have time for design. So this is obviously just carelessness or negligence. So if you know you should apply best practices, but you just don't do it deliberately, then it's not a surprise if you have bad results at the end. Here, reckless and inadvertent. What's layering? So this is pure incompetence, right? If you are not even aware of best practices, then you can never have a good result at the end. This is one of the good cases for technical depth. So we are acting prudently and deliberately. We must ship now and deal with the consequences. This is one of the classical cases where we don't have enough time, so we consciously decide to take a suboptimal solution so that we can deliver features, but we are aware of it and we have probably a plan how to fix it later. And this is a very specific case for software development. Now we know how we should have it done. So we are acting prudently, but nevertheless, we create inadvertent technical debt. And this is just, this knows every developer. It just happens all the time in software development that you know how the good solution should have been just after a while. Okay, this is the explanation of technical debt, and what we actually try to do is to bridge a gap between these technical issues and the managers, and the technical debt metaphor suggests that technical debt is similar or comparable to financial debt. And well, let's see if it really is the case. What we have tried to do is to create a mapping of this quadrant to financial debt and see if we can find examples for all the cases. Just a small reminder, what is financial debt about? So it's obviously about credits or loans. So it's about borrowing something in the present and paying interest on it later, right? So when I take technical debt, I take some credit by producing a suboptimal solution so that I can deliver features now. And the interest that I have to pay on this suboptimal code is just the extra work I need to do, for example, because this suboptimal code is misused in the meantime, or it is additional cognitive overhead that occurs always when I'm losing the context. So when I'm here and now in the code, I know how it should have been done in a better way. But if I have to get back into it in 1 week, 1 month, half a year, it will take more time because I lost the context. And this is exactly the interest. So let's start by filling in. Can we have financial debt if we act reckless and deliberate? Well, there is a possible example. We can get more and more credit cards, interact with them, and produce debt. So it works. This is the good case for the classical case for financial debt. Well, I need to live now. I don't have enough money, so I get a credit, but I have a plan how to pay it back. Now this case is a little bit difficult, so handling reckless and inadvertent. Can I have financial debt inadvertent? Don't care about the example on the slides. Actually, I have a much better example from real life. It really happened to a friend of mine in his company. They had a workshop where they presented some CPU-heavy computations, and his colleague ordered some computers in the cloud, and the workshop was planned like for 2 days, but he forgot to cancel the subscription, and it went on for more than a month and produced costs over 100,000 euros. So he lost his job at the end because of this. Now, let's get to the last example. Can we act prudently but inadvertently produce financial debt? So can we have credits or loans? Can we take loans even so inadvertently, even so we are prudent? Can anybody imagine an example for this? Exactly. It's very hard to imagine an example of financial debt that we take unconsciously, even so we are acting prudently, right? And this is also the reason why the entire metaphor doesn't work. That's why the unequal sign here in the middle. And that's actually a pity, because this unintentional technical debt is actually the most common and harmful in software development, and it's really very specific for software development. This is what we actually try to explain to people, to non-technical people, with this analogy. But exactly where we need it, it doesn't work, because non-technical colleagues quickly realize that it's not a real money problem, because there is no such case in the financial world, so they conclude that we don't know what we are talking about, or that we are using the wrong terms. So what we have to do is we have to translate our message into business results. And how to do it? Here is another picture from Martin Fowler. I don't want to go into details of this picture. The important points here are the differentiation between output and outcome. So what Martin Fowler tells us is we have to focus on the impact that technical debt or technical issues have on the entire project, or even on the customers, and not on the technical low-level output. And of course, it's not trivial to connect the technical debt to this high level of output in a project. But nevertheless, let's assume we could do it. So how communication could look like between developers and managers if we could connect technical debt to business outcomes. The developer could say, okay, we have to give discounts on our sales of 1% last month. And discounts is something that is interesting to the manager, because he or she is worrying about it. So she could ask, okay, what's the problem? And then we could argue and say, well, our system is filled with technical debt, and what we can do about it, we can spend some weeks to fix technical debt, we can halve the error rate, we can halve the discount that we have to give, but instead we have to postpone certain features. And the blue highlighted parts of the discussion are exactly the output that Martin Fowler is talking about. Of course, as already mentioned, of course it's not trivial to link technical debt, these low-level issues, to such a high level that matters on the business level. Nevertheless, we will present ways how it can be done. And before I pass over to Enes, just as an interim conclusion of what I've been saying so far, don't use these technical explanations, these technical definitions for technical debt when you're talking to non-technical colleagues. It's sometimes, for us developers, very tempting to do it, because these definitions are correct, they are good, they are not wrong, and we love them. And actually, we are showing such kind of definitions in other talks when we talk to technical people. But the problem is that they work only in one direction. So they make sense only if you already know what technical debt is and what is the problem behind. Then you look at such definition and you think, wow, it brings it to the point. But it just doesn't work if you are not aware of the problem. It does not work with managers, non-technical managers. Enes?
So thanks to Konstantin, we have now a better understanding of our problem, and let's now talk about the solution approach. How can we do it better? So, oops, sorry.
It's other direction.
Okay, it works different direction. Okay. Then one way could be the pictures. We brought you a picture. This is a picture that that the mess you left after you prepared a meal for your guest. You invited some guests and you prepared an excellent meal, and then when the dessert time comes in, you shouldn't let your guests into your kitchen because you always leave some mess behind you. It's quite analogous, it's quite similar in the software development area. We deliver excellent features, and then we sometimes we leave some mess behind us. So this is a pictorial way to show our problem, show the technical debt. But unfortunately, we have to use some hard facts. We have to use some serious words to show our problem to the technical people, to the non-technical people, to have a budget or all the resources that we are going to need to resolve our problems, to clean this mess. So what would be those hard facts? I believe those would be monitoring the technical debt, monitoring the symptoms of technical debt. How can we monitor the symptoms? We should measure the non-productive cost of our engineering work. I mean, we sometimes deliver features and we spend our effort on the feature work, but sometimes we spend our effort on the non-productive works, such as defects or bugs or anything else. We need to also evaluate or determine the interest rate. That means over time to time, we will need more effort to deliver new features with that mess we left behind us. So this all has to be measurable so that we have those hard facts to go to the management team, to have the things that we are going to need. So how can we do that? Luckily, we have lots of extremely high numbers of different data sources in software engineering area. We have code repositories, which is now the standard for almost every software project. We have the issue trackers, which is also now a standard for the vast majority of the software development projects. And we can add different data sources like DevOps tools or test coverage tools or any tools that you could imagine. And the most important thing here is the big black arrow here. We need to associate our commits, our code repository, to the issue trackers. Once we have that connection, once we have that association, we can do a time-based analysis over commit to commit, over sprint to sprint, over release to release. So how can we do that? We can do that easily by adding issue IDs to our commits, by using feature branches, by using pull requests and connecting those pull requests to the issues themselves. It's quite easy and feasible. We can do that. We can manage to have this data. So once we have this data, we can measure our development efforts. I believe we do it in a very wise and pragmatic way. We add all the change of lines. We have added lines. We have modified lines, which we weight by 2, because before you modifying a line, you need to understand what it does. Before understanding it, you cannot change it. It also stands for the deleted lines. You need to understand the line before you delete it. So all of these things makes us able to measure our effort. And once we have the connection between our lines of change and the issue types, we can measure the effort that we spend on defects or features. And we can create some connection, we can calculate some KPIs, some key performance indicators about technical debt, about the non-productive work that we spend over time across commits. Of course, it has limitations. One can object and says that there's an edge case, I spent whole day on Stack Overflow or with ChatGPT now to trying to find out the problem about my code, and then I end up on a one-liner solution, one-liner fix. But from our experience, it's always proportional. Somehow it's always proportional to the lines of change. So, of course, there can be another edge cases like automated changes. You add some license headers or reformatting or anything you can imagine. Of course, from your experience about your project, we can eliminate those effects from our analysis. So, in the next step, we will have a list of possible KPIs, possible key performance indicators about technical debt. We have these bugs and features per iteration, per release. We will get that from any issue tracker for free, and we will measure the maintenance effort that we already talked about. It will be our non-productive work. And then we can also calculate the percentage of the development effort with the maintenance effort and the feature development effort. And we can also calculate the interest rate here. The interest rate is how much the additional work that we spend on developing new features. I mean, for new features, we generally expect added lines of code, but sometimes the code be moved back and forth. This is the feature effort effectiveness. Actually, it is non-effectiveness because you need to move your code anywhere else before you change it. It needs to some refactorings in it. And then we also extend of follow-up bugs. I mean, we can have several fixes after a bug fix. I believe most of the people in this room are familiar with this situation. You create a fix and you push it, and then you have 3 or 10 different bugs comes from that fix. So these are the actual symptoms that can be observed, that can be measured by a simple analysis, by the connection between issues and the commits themselves. So what can we do now? We need to reduce this technical debt. We know that we probably have some technical debt. We need to do something to reduce that technical debt. How can we do that? We firstly need to identify the hotspots in our software project. The source code files or the features, we need to find the hotspots with highest bad KPIs, technical debt KPIs. And then we, of course, need to connect those technical debts to the features. I mean, which technical debt will prevent us to deliver these features, these important features. This tool is about the where do we have this technical debt, where do we need to work on to resolve this technical debt. And then we need to also decide to where. When are we going to deal with it? To this, we need to predict our effort that we are going to spend on resolving technical debts, or the maintenance effort in case we don't resolve these technical debts. Sometimes we can afford the maintenance work instead of technical debt because it would be maybe more feasible to deal with maintenance work. And then, of course, we also need to decide how can we do it, or what are we going to need to do to resolve these technical debts. So we need to focus on root causes. We need to find the causes of technical debts to reduce this technical debt, to clean those messes. So to be able to give an example for root causes, we have here bubbles as files, and the bubble size are the maintenance effort that we spend on those files. Here the x-axis is the code complexity, and the y-axis is the code applications. So here on the brown bubble, we have a huge code complexity, thus we have this high effort of maintenance. On the orange here, we have a mixture of code complexity and code applications, but I believe it's mostly about code complexity as well. So the left above is only probably about code applications, but it's a medium effort, medium maintenance effort. So this is an example of the root causes. This is our general approach. We correlate these symptoms of technical debt, such as maintenance effort, with the potential causes, such as code applications or the code complexity. So we find the potential root causes. This could be bad code quality. You can get it from tools like SonarQube. We have our bad architecture quality. I will show you some examples from our detangle tool. We can measure the gaps in our documentation easily. And we have another knowledge asymmetry analysis in our detangle, which is my favorite. I will also talk about it. And we can have insufficient code reviews, lack of code reviews, or we can have low numbers of tests or insufficient engineering processes. A banal example would be a test is a test added after all bug fixes, or even it's a part of your engineering process at all. So we have the potential root causes, and we have the KPIs that we measured already. Here is an example of our architecture quality metrics from our detangle tool. We take the single responsibility principle at a higher level, to an architectural level. On the left image, we call it feature cohesion. We have a file here which has contributed two different features. So if you change something about feature A, you need to be careful about feature B. You can break it. It's too important. So it's a potential cause of possible bugs. And on the right image, we have a more complicated structure. We have something we call feature coupling. We have different features again, but also different files. We have file 3 and file 4, which have contributed to these two features, maybe more features, several features. So when you change something about feature A, you need to be careful about feature B, and you will probably need to change something on file 4 as well, not only file 3. So this also can cause some bugs and problems, or let's say technical debts. So this is another example. This is an exact screenshot from our detangle analysis. It's an analysis of famous corona warning app of Germany, our team has analyzed it in 2020, I suppose. Here is we have these circle segments as features, and the features with labels are the risk calculation features, as far as I remember. Yeah, risk calculation features, and we have these couplings between those features, which is quite normal because they are in the same cluster, they're in the same area, they are risk calculation features. But what we have here is also the asymmetrical couplings. We need to eliminate them because they may cause some safety problems. Let's say these risk calculation features are safety critical features. We need to reduce the dependencies with these safety critical features and the other features that we don't know right now, but probably not safety critical. So here it is our another metric, which is our another analysis, which we call knowledge distribution analysis. So here we have squares as files and small circles. I'm not sure if you can see them as developers in our project, and the links between the features and the source files, of course, the commits. This means this developer has contributed to those files. So here we have some different patterns. This big one is something we call knowledge island. It may seem perfectly because we distributed the work in a very good way. But when this developer decides to leave company, we are screwed. Because nobody knows anything about this part of software. We will lose all the know-how on that area. So to resolve this problem, literature says it's the best way to share knowledge, to work at two people together. No more, no less, just two people. So here we have this pattern. These two developers here shared the knowledge in this area. And in this area, we have very less number of bugs. And when more people comes in, they work in a very chaotic way. Here is the third pattern. They don't know. I know the code ownership doesn't have a good reputation, but this is what it is. There's a chaos here, and there can be serious problems. I mean, have you heard about diffusion of responsibilities? It's a phenomenon from psychology. The more people in a situation, in an emergency situation, for example, the less probability of their reaction. For example, if I had a heart attack here, for example, let's say we are only 3 people, you will probably react immediately. But when more people comes in, you will probably wait for the others. For example, with 100 people. This can also occur to your software project. So the point is here not to control people, but provide them a balanced workspace, a balanced team structure. So we have seen the problem, we have seen the symptoms, and we have found the root causes. And we will probably eliminate them. But what we do, what we need additional, we need to show the pays off, show the value of eliminating technical debt. We need to show the difference to the management, to get additional money, to get additional people, to get additional resources to eliminate all the technical debts. So to be able to do that, we need to measure the actual effort that we spend on technical debt that we spend on refactorings. So to do that, we need to introduce the technical debt as separate tickets, as separate ticket types. And then we can also show the positive trends. I mean, we already seen the measurements, seen the symptoms of technical debt, and we can show to the management those symptoms are decreasing. This is too important. But as a concrete recommendation from our take, or let your developers take the improvement work, the refactorings as tickets. This is too important to show the value of the refactoring. So here is our latest slide, the summary of our talk. We have this atomic model of technical debt. We have seen the business consequences, and then we measure the KPIs, we measure the symptoms of technical debt, and then we find the root causes, and finally we will smash the technical debt down completely. No, I'm kidding. It's not feasible. It will be always there, but the point is we need to find a way, find a reasonable and understandable way to deal with it. So thank you very much for your patience, and here is our fancy QR code that you can download our slides from our website. You can also use this link here. So if you have any questions, you can, I think we have 4 or 3 minutes. You can ask now, or you can catch us around the JCon. Thanks.